Hello there, Mr. Sutton here, bringing you this lesson on total distance. In this one, we'll be finding the total distance traveled by a particle, which is a little bit different than its displacement, and we'll also be finding the average velocity of a particle on an interval. For a warm-up, we have a graph representing the velocity in meters per second of some particle moving on the x-axis. We want the net distance and total distance traveled on the interval from 0 to 10. Pause the video, give it a shot. All right, so we're finding area under the curve here. We have a rate of change of position, so we want to find total change in position, or at least that's kind of our starting point. Now, we've got different types of areas that we're going to be adding together. We have two positive areas, and then there's this negative area below the x-axis. When you're doing net distance, the sign of the area matters. So we've got the area of this first triangle. That's going to be a base of 2 times a height of 3 over 2, or 1/2 times 2 times 3. Then we have this trapezoid. We have a base of, 5, a base of 3, so we're adding those, 5 plus 3 over 2, and then we're multiplying by height of 3. Since this is under the x-axis, this is going to be negative area. And then we have this last triangle. We have 3 times 3 over 2 for that one. And then if you wanted to simplify all of this, this is going to be, 3 minus 12 is negative 9, plus 4.5 is negative 4.5 meters. Okay, so how does this differ from total distance? Well, with total distance, the direction that we're going doesn't matter. Like this spot down here where we turned around because we had a negative velocity, we don't care that you were walking the wrong way. All the area is treated as positive. So the only difference between net and total distance is going to be we're going to make this middle term here positive. And then adding all this up now, we still have 3, but this is going to be plus 12 and plus 4.5 for a total of 19.5. For this next example, we have a particle moving along a coordinate line with a velocity function for t greater than or equal to 0 given as follows. This will be 6t squared minus 6t. We want to find the total distance traveled on the interval from 0 to 2. So pause the video and give this a first attempt. Did you end up with an answer of 4? If so, then you made a good try, but you were missing something in between. So whenever they're asking for total distance and you can't see the function, you really do need to check for sign changes in the velocity. So we're going to go ahead and check for those direction changes by setting this thing equal to 0 and solving. We can take out a 6t when we do that, leaving us with t minus 1 inside. So we then have critical values of 0 and 1. Let's go ahead and do a little sign analysis to see what the signs are for our velocity. So 0 we don't have to worry about because we're asking about time greater than or equal to 0. So really it's just 1 we have to check. If we plug in something to the left of 1, like 1/2, that would be a positive times a negative, so negative overall. If we plug in something bigger, like 2, that would be a positive and a positive, so positive overall. So we do have a direction change for our particle because our velocity has different signs at different points along this interval. So how do we deal with this? Well, if we just take the integral of this directly from 0 to 2, we're going to be throwing in some negative distance along with positive distance. And that's not going to tell us the total distance traveled. It's going to tell us the net distance. So to fix this, we need to split up this integral and use absolute value for each piece so that we're making sure all area under the curve counts as positive area. So we're going to have the integral from 0 to 1, because that was our critical value, our sign change value of our velocity, plus the absolute value of the integral from 1 to 2 of the same function. So at this point, let's go ahead and take some antiderivatives. We're going to have this bumping up to third power. Dividing by 3, we have 2t cubed minus, this will be 3t squared. So we're going to evaluate that from 0 to 1 for that first integral. And then from 1 to 2, same antiderivative there for the other integral. Okay, let's go through and split these up. We're plugging 1 and 0 into this expression and subtracting, all inside one big absolute value. And then we're going to plug 1 and 2 inside the same expression and subtract, all inside another absolute value. And we're adding those absolute values together because we were adding them together up here. Going through and taking a look at each one of these, we've got, let's see, this 0 stuff is just going to be 0. Over here we've got 2 minus 3, which is negative 1. So the whole first bracket here ends up just being absolute value of negative 1. Next, for this one, we still have negative, actually not negative 1. This is negative 1 over here. But over here we've got 16 minus 12, so that's 4, minus negative 1, so that's a total of 5, and we're adding the absolute value of 5 then to the absolute value of negative 1. So this ends up coming out to 1 plus 5, which is going to be 6. So you were pretty close. You just had the wrong sign on that first distance there. For this calculator-based problem, we have a particle going along a coordinate line with velocity given by this v function right here over this interval, and we want to find the total distance traveled on this interval. Okay, so if you have a calculator, one way you could do this is figure out the direction changes by seeing where velocity is 0 on your graph, and then split up your integral using your fnint function to take those antiderivatives, and then just use your zeros for velocity as your limits of integration. Now let's see what this looks like on a graph. So here I am on my grapher in my y equals, and feel free to pause the video and take a moment to graph this out on your own. To really get a good window on this, I'm going to enter the range of values they gave me. So we're doing, let's see here, pi over 2, and that'll be my x min, and now my x max, I've got 2 times pi. And then let me do zoom 0 to see what this looks like. So here's my velocity graph. So I need to figure out where this thing is crossing the x-axis and create a separate integral and take the absolute value of each integral every time this thing crosses the x-axis and the velocity is telling us that we're changing direction. Yeah, have fun with that. There's got to be a better way. So rather than taking all these different integrals and forcing each of them to be individually positive, another way you could do this, if you have a calculator, and only if you have a calculator, is to integrate with a single integral, but put an absolute value around the integrand itself. Now, we don't really know what to do with that if we were to try to do it by hand, but your calculator has no issue with this. So in this case, we would have the integral from pi over 2 to 2 pi, and I'm just going to do now absolute value of v of t dt. And let's go ahead and put this in the calculator. So here I am back on the calculator. I've already off camera done Math 9 and entered my limits of integration. But now I'm going to do, let's see, alpha window, and that pulls up this little menu from which I can select my abs function. And I'm going to do alpha trace and put y1 in there, and then I'll do dx. So now I'm just basically taking the absolute value of velocity inside the integral and press enter. And we're going to wait for it. Wait for it. It does take a while because you're basically forcing your calculator to turn all of these things positive and then add everything together. So that's quite a computational task that you're asking it to do. But if you think about it, it's quicker than figuring out all these x-intercepts and creating a different interval, a different integral for each of those. So at the end of all of this thinking, our calculator eventually gives us, dramatic drum roll please, 0.883. Wow, I couldn't have timed that better. There we go. For this last example, we're not finding total distance anymore. This time we've still got a velocity function, but we want the average velocity on the interval. So before, when we were finding average velocity, we were actually given a position function over an interval, and we had to find two different positions and take the average rate of change between them. But now we have the function we're actually trying to average. So what can we do in this case? Well, how about we just take the average value of the velocity using our average value function. So we're going to have 1 over 9 minus 4 in general, 1 over b minus a, times, we have an integral now. Well, you know the rest. Pause the video and finish this one off. So times the integral from 4 to 9 of the velocity function, which I'm just going to write as v of t dt. Calculator time. So I've got my velocity entered in the y equals, and then I'm going to put all of that in an integral, 1 over 9 minus 4, 4 to 9. Let me do alpha trace y1 in there. dx, gives me an average value of 16. Probably could have done this one by hand. So thank you so much for going the distance with me on this lesson. Till next time, Mr. Sutton signing off.